hypothesis is known as the research hypothesis. It's the question that you're trying to research on, right? And then you have the other one is the test. These are things I already talked about yesterday, so I'm not going to describe one more time. Test statistic is a function of the data. It's normally denoted like this. It's a function which I call capital T of the data x1, x2 to xn. And this function is used to determine whether to reject or not to reject the null hypothesis, right? And I described that in more. I described this in more detail yesterday, which you were in the lectures yesterday. The next one is the acceptance rejection region. All right, this is, I will describe it one more time. I'm not sure whether what I described yesterday was clear or not. I'm not sure. So let me describe it one more time, guys. So what you have here is two spaces. The first space is the sample space, and it contains all possible configurations of the data. Right, it contains all possible values for the data, right? So each of these points is a set of data. And then you have another space here, and this space is obtained by applying the function, the function t, which is the test statistic. So you apply the function t to each of these data points, and you get the new space. Right? Right? So when you every point in the sample space is mapped into a new space looking like this. Now this space can be divided into two regions. The region I shade in red, right, and the region which is not shaded. The region that is shaded in red is known as C, right? And the region that is not shaded is the complement of C, right? And basically the C is the rejection region, and or sometimes it's also known as the critical. It's also known as the critical region, and the complement of C is the acceptance region. So the rule is as follows. That is, if T is the function of the data, if it maps the value that is mapped M-A-P-P-E-D, the value that is mapped by T belongs to C, belongs to the set C, then you reject the null hypothesis, right? If the data value or the data value mapped by T does not belong to C, then you accept the null hypothesis. You understand, guys, what I'm talking about? Because every data point in this space is mapped into this space. Depending on where it goes, whether it goes here or here, you either reject or accept the null hypothesis. Right? That's it. Right? Oh. All right, guys. Is that clear, guys? Yeah. All right, the next thing I'm going to talk about is when you do this kind of things, because we are we are only humans. We are bound to make some errors, and there are two types of errors that you can have. One is called type 1 error. The other one is called type 2 error. Right? Now, let me describe to you how these two errors arise. All right, there are two things you need to consider, guys. The first is the decision, right? The decision is, there are only two possible decisions you can make, right? One, either you reject H0 or you accept H0. These are the two possible decisions that you can make, right? Either reject or accept. But you also have something known as can you read this, guys? Is state of nature, right? I have written like this, sorry, because either H0 is true or H1 is true, right? State of nature is something that beyond, we don't know what is something controlled only by the God, right? The God knows whether H0 is true or H1 is true. We are only human beings. We don't know, right? Right? So there are only two, either H0 is true or H1 is true. So now you have a square right? You see what I've done? There are four possible outcomes you can have, okay? The first outcome is that H0 is true, but we reject the null hypothesis. Is it the correct thing to do? No. So this is not something that you want to do, but it's unavoidable. It's unavoidable, all right? The second is H0 is true, but we accept. This is the correct thing to do, right? The third one is H1 is true, and we reject the null hypothesis. So this is, once again, a correct thing to do. The fourth one is H1 is true, but we accept H0. So this is, once again, an incorrect thing to do. So of the four possible events, of the four possible outcomes, two of the outcomes are things that you don't want to happen, but they are bound to happen, right? And the remaining two outcomes are things that you would like to happen, right? That is this one and this one, right? Now, this outcome, that is, you reject H0 when H0 is true, is known as right? This outcome is known as the type 1 error. And this outcome, where you accept H0 when H1 is true, is known as the type 2 error. Okay? You guys okay? Yeah. So that's the thing here, guys. So the type 1 error and the type 2 error, they are bound to happen. It doesn't matter how superhuman you are, you cannot avoid type 1 error and type 2 error from occurring, right? They are bound to happen, okay? Okay? So there are a few things I need to define, guys. So let me say one more time that type 1 error is you reject H0 when H0 is in fact true. Type 2 error you accept H0 when H1 is in fact true. Okay. Okay, guys. So these are the two definitions of type 1 and type 2 errors. Now I also need to define alpha. Alpha is the probability of type 1 error. And beta is so these are common notations. Alpha is is also known as the significance level. All right, alpha is also known as the significance level, and beta is the probability of type 2 error. Right? Ideally, in the ideal world, which is never there, right? The world is never ideal. Ideally, we would like alpha and beta to be equal to 0. But in practice, in practice, in the practical world, alpha and beta can never be equal to 0. Yeah. So the question for the statistician is that how to minimize the value of alpha and minimize the value of beta, right? So the question is, how do we minimize the values for alpha and beta, right? So in other words, come up with a test that gives the smallest possible value for alpha and the smallest possible value for beta. Now the answer to this question is in the lecture notes. If you go to page 34, which is the last page of the notes. But we're not done yet. We've got a lot more to cover, guys. Okay, guys. Sorry, guys. If you look at page 334 of the lecture notes, there's something known as the Neiman-Pearson lemma, right? And what this result gives you is a test. This result gives you a test that has the smallest possible value for alpha and the smallest possible value for beta. Yeah? So I'm gonna write down the test in a minute. Okay, consider testing the null hypothesis that theta equal to theta 0 versus the alternative that theta equal to theta 1. The word most, the two words that you need to remind yourself is most powerful. It means, the word most powerful means that it has the smallest values for alpha and beta, right? Okay? Right? So the test that will reject the null hypothesis if the ratio of the likelihood at theta 0 to the likelihood at theta 1, which is this divided by this. Remember guys, we did many examples on ML likelihood functions, right? A likelihood function is the product of the density function. So this is equal to this, and this is equal to this. Yeah? So if you take the ratio of the two, and let it be less than a constant k, right? And this rejection rule, I mean, what I have written down here is a rule for rejecting the null hypothesis, will have the smallest possible value for alpha and the smallest possible value for beta. And this result here is known as the Neiman-Pearson lemma, right? Okay? And we will do some examples on this later on. But before that, I need to, before I do examples, I need to introduce one more thing. I need to introduce, you've probably seen this before, guys, something known as the power function. Right? Now, okay, suppose we are testing the null hypothesis that theta equal to theta 0 versus the alternative that theta is not equal to. Okay? The power function the power function of theta is defined by the following. So this, guys, this is capital pi, okay? This is the definition of the power function of theta, right? So it's the probability of rejecting the null hypothesis given the value theta, right? Now, if you plot this, because let me show you. Just be patient with me, guys. I'm not good in drawing things. All right. Typically, I mean, I must use the word typically, if you plot pi of theta versus theta, it will look something like this. Yeah? It will look like a bathtub shape, right? With a minimum occurring around over here. Now, can you guys see why it should look like this? Why? Why is the reason typically it should look like this? Because, let me explain why. This point here, right, that is the height from is equal to pi at theta 0, right? Now, pi at theta 0, by this definition, is the probability of rejecting H0 given that theta is equal to theta 0. Now, can you tell me now what this is equal to, guys? Alpha, exactly. So this is equal to alpha, which I defined just a few minutes ago, guys. If you look at this, guys, here, alpha is the probability of type 1 error, which is the probability of rejecting the null hypothesis when it is true. Yeah, which is the probability, which is the same as this. Now, I said to you just a few seconds ago that we like to minimize alpha as small as possible. And that's precisely why you see that the lowest point of the graph is here, because we want alpha as small as possible, right? Okay, that's why it looks like the lowest point is attained at theta equal to theta 0. Now, we also want beta. We also want beta as small as possible. Beta is the probability of type 2 error, which is, I'll come to that in a minute, guys. Now, let me explain. Let me take a point over here, guys. Now, this height here, right? If this is the point, say, theta, right? This is equal to pi of theta, which is the probability of rejecting H0 given that theta is not equal to theta 0. Can you see this? That this height here, there's the distance from this point to this point is the probability of rejecting H0 given, because theta 0 is over here, guys. Obviously, this is not equal to theta 0, right? So this is the probability of rejecting H0 when theta is not equal to theta 0. Now, if I ask you, if this distance is equal to this, then the distance from this to the top level, which is 1, what would this be equal to, guys? If this distance is the probability that you reject H0 when theta is not equal to theta 0, this will be, I mean, the distance from this point to this point will be just, let me write it down, guys. It will be 1 minus the probability of rejecting H0 given that theta is not equal to theta 0, right? Because remember that this and this must add up to 1, yeah? That this distance and this distance must add up to 1. So the distance from this point to this point is simply 1 minus this probability, yeah? And which is the same as saying the probability that you accept H0 when theta is not equal to theta 0. Because it's by the negation rule, right? What the negation of rejecting H0 is accepting H0, right? So now, if you look at beta one more time, what you have here is precisely equal to beta. Remember, we defined beta as the probability of accepting H0 when H1 is true. And what you have here is precisely equal to beta, right? And that's why that these distances, the distances from this point to this point, the distance from this point to this point, they're getting smaller and smaller as you go further away from theta 0. Because you want the beta to be as small as possible, as well as the alpha, yeah? That's why all these distances, as you go further away from the center, from theta equal to theta 0, they're getting smaller and smaller and smaller, because you want beta to be as small, yeah, as possible. So that explains the shape, the typical shape of a power function, right? The shape is constrained by the condition, by the desire that we want both alpha and beta to be as small as possible, and that drives the shape here, right? Okay. Now, one more thing I need to say is, suppose there are two tests, because when we talked about parameter estimation, we had the issue of selecting between two or more estimators, right? You remember that, guys? We did several examples on that. And how do we select the best estimator? We consider the bias and we consider the MSC and see which is unbiased and which is consistent. Right? And the same thing applies when it comes to testing. Right? It's possible that you can have, for testing the same hypothesis, you can have multiple different tests. You can have 2, 3, 10, so on, right? But how do we select the best one? How do we select between, if you have more than one, how do we select which one is better and why? Okay, that's what I'm going to talk about now. Suppose right, this is pi 2, guys. This is pi 1. Okay, let pi 1 and pi 2 denote the respective power functions for the two different tests. And what to do next is to plot them. I'm not. So I'm going to plot. Suppose one of the power function, no, this is not a good one, but suppose it looks like this, all right? And suppose the second one looks like this, right? So this is the point 1, this is 0, this is theta. Now, suppose this is pi 1 of theta, and suppose this is pi 2 of theta. Now, if I ask you, like, which of the tests is better, what would you say? Of the two power functions, which one is better and why? Yeah, clearly pi 2 is better in this case, because the reason pi 2 is better is because it has smaller. Remember, these here are the values of beta, right? The value of beta for the second test is smaller, right? And therefore you would choose the second test, right? So in this case you prefer test 2 to test 1. All right? Yeah. But it will not always be clear cut like this. Sometimes in practice, when you have multiple tests for the same hypothesis, it will not always look like this, right? I know I have deliberately used an example where one of the tests is clearly better than the other, but in practice, right, there may be cases like there's certain regions of the parameter space where one test is better, and other regions of the parameter space where the other test is better. You know what I'm saying? Yeah? Okay? All right. Now, okay, this is a simple question. If right, if there is an ideal test, this is I mean, I know there's nothing like ideal in the world, but if there is an ideal test for this versus this, how do you think the power function will look like? Yeah. Now, if I ask you to draw theta 0, this is the line 1, right? This is 0. Now, how do you think the power function will look like, guys? If the test is ideal, that is.
It could be continuous.
Yeah, exactly, yeah. So it will be, it will, it will look like this, except at the point theta equal to theta 0, it will be equal to 0, right? Yeah? So the power function is kind of, it will be 1 everywhere, except at the point theta equal to theta 0. All right, so basic issue in the math issue, so it will be equal to 1 if theta is not equal to theta 0, and 0 if theta equal to theta 0. Yeah, but this will never happen in practice, as I said before, right? You will never have an ideal function. But the reason I have asked you this question is because of this, guys, right? I said before that the Neyman-Pearson lemma gives the most powerful test. The two keywords are the most powerful. What it means is that if you plot the power function for the NP test or the Neyman-Pearson test, right, what you will get is the closest that you can get to the ideal function, right? In other words, if you suppose the power function for the NP test looks like this. Now, what the two words here, the most powerful, what they mean is that you cannot have another test. You cannot have another test that is closer to the ideal one than this one. That's what it means. Is that clear, guys? Yeah. So this is, so if this is the pi of theta for the NP test, right? All right. If this is the pi of theta for the NP test, you cannot have another power function that is closer to the ideal one than this one, right? So, and that's hence the word most powerful, meaning that that's the most power you can get, right? Okay. Is that clear, guys? Yeah. All right. Now, I think that's all I wanted to talk about with respect to power. Now, I haven't done any examples today, guys. So let me see if I have time. Let me do an example, guys. Okay. This is from the examples booklet. I hope you have a copy of this, guys. Because there was somebody yesterday who said that he hasn't got a copy. So if you don't have a copy of this, guys, please come to my office. I've got plenty of copies still left in my office, guys. So if you still don't have a copy of this, just come to my office, guys. All right? So I'm gonna do example 75. You have all right. Case 1. You reject right. So there are three parts to the question. The first part is we reject the null hypothesis if this is the case, right? And we want to find alpha, beta, and the power function. So I will just only do the power function part and let you do the others by yourself, right? Now remember, the power function is defined as what? I said that a minute ago, guys. You reject H0 given the value for mu, right? So so it's the probability that root of n yeah. Okay. Now how would you work this out? Any ideas, guys? How to work this out? Now, to work this out, the first thing you must realize is that mu 0 is not the true population mean anymore. The true population mean is mu, not mu 0. So the first thing you should do is to change mu 0 to mu. How can you do that? Is to okay. Now, I'm going to group these two terms, guys, and take them to the right hand side. Okay, so it will become right. Now, let me ask you a question. This is testing your memory, guys. Do you guys know the distribution of this, guys? You would know if you've been come to. I think we did this stuff in week 1 or 2 of the lectures. Do you guys know what distribution this has? Standard normal, yeah. Why? I hope everybody follows. All right, let me explain in a couple of steps why it is. Because X bar, remember, if you look back at week 1 or week 2 notes, you will see that X bar has the normal distribution with parameters mu and sigma squared by n, right? Right? Now, if you subtract mu and multiply it by this, you get the standard normal, as you said, right? Okay, so this will become the probability that a standard normal, yeah, is greater than Z alpha minus yeah. Now, you see here, now I dropped the conditioning here because the only place, the place I have used the conditioning is over here, right? To argue that this has the standard normal distribution, I have used the fact that the true population mean is equal to mu, right? So since I have already used it, I don't need that conditioning anymore, right? So the conditioning is not here, okay? So this can be written as the probability that a standard normal by the negation rule yeah, and finally this is equal to phi. Capital Phi is, as you know, is the CDF of standard normal, equal to Z alpha minus root of n mu all right. So this is the power function for the first part. Sorry guys, sorry. So this is the power function for the first test, right? Is that clear, guys, or no? Yeah? Yeah? All right, now to find, to find alpha and beta. Okay, let me show you. Alpha, remember, alpha is the probability of rejecting H0 when H0 is true, right? So which is what? Which is pi at mu 0, right? Alpha is the power function at mu equal to mu 0, right? So it will be 1 minus phi so this is 1 minus phi of Z alpha. And beta is the probability of accepting H0 when H1 is true. Yeah? So it's the probability of accept all right, which is 1 minus the probability of rejecting H0 when H1 is true. All right? So it's 1 minus the probability of rejecting H0 because if you look at the question, guys, here, we are saying that the alternative is mu is greater than mu 0, right? So this is 1 minus pi at mu for mu greater than mu 0. Yeah? This is simply 1 minus this, so it becomes phi of Z alpha minus root n for mu greater than mu 0. Is that clear, guys? Yeah. So this is the expression for beta given that mu is greater than mu 0. All right? Yeah? All right, that's only the first test. Now the second test, where are we now? Yeah. So we did this one so far. The second one, so this is test number 2. Test number 2 is that we reject H0. Sorry, guys, is this one here. Reject H0 if x1 minus mu 0 divided by sigma is greater than Z alpha. Right? Okay. In this case, the power function for mu is this, yeah? The probability of rejecting H0 given the parameter mu. Now, one more time, you must realize that the true population mean here is mu, not mu 0. So the first thing you must do is to change this to mu. Right? Then group these together and take them to the right hand side. Right. Now one more time, the distribution of x1 minus mu divided by sigma. Remember, we are assuming that each x is a normal distribution with parameters mu and sigma squared. So this must have clearly the N01 distribution. All right. Now, one more time, I have removed the conditioning because at this step, to argue that this has a standard normal, I have used the fact that the true population mean is mu, and therefore the conditioning is not needed anymore, right? All right. So this is simply 1 minus phi So this is the power function for the second test, guys. And I assume you know how to work out alpha and beta for this, right? In the same manner as for the first test. All right, guys. I'll see you guys tomorrow if you're coming to the example class. I'm really disappointed with the number of people turning up for the example classes. I would like more of you coming to if you haven't been to the example classes yesterday, and you please turn up for the ones tomorrow. Tomorrow, 11 to 12 and 4 to 5. Okay?
Is that the same as take n equals 1?
Yeah, it's the same as n equals 1, but here you have the sample mean there. Here you just have one variable x, but here you have a sample mean.
Alright, so this is for sample and this is for only one.
Yeah, one and so on.
Alright.
Yeah.
Thank you.
You come, if you have more questions, you can come and see me in my office anytime. That's nice. Good.